Okay, so let's start studying ideal gases now. We're going to start with ideal gases, and an ideal gas is just a model for a gas, and f- it's going to be thought of particles that are inside a container and they don't interact with each other. They occasionally collide, but they don't interact with each other and they collide very little, and they are inside a container. So we are going to think of them as hard spheres that fly through space, occasionally bouncing off each other, and they don't lose any energy as they bounce from each other. So this is the ideal gas. And experiments show that this is a very good model for many gases in real life if the density is low and the temperature is well above the condensation point. So there are four quantities that we are able to measure when we work with an ideal gas. We have the pressure, the volume, the number of moles or number of particles, either one, and the temperature. So these are the four quantities that we are able to measure, and they are related. They are going to be related by this equation here, which we call the ideal gas law. And it says that the pressure times the volume is equal to the number of moles times R, and R is this constant here. Okay, it's a universal constant times R times T. This is the ideal gas law. It can also be, this is written in terms of moles. It can also be written in terms of the number of atoms, and in that case, the pressure times the volume is equal to N kV, and kV is just this other constant here. It's called the Boltzmann constant times T. So either of the two equations give you the same information about the ideal gas, and this is called the equation of a state of the ideal gas. Equation of a state. So before we go into these questions, let's look at a little simulation to see uh, how an ideal gas behaves. So here we have a container. This is our container, right? This container here. And let's add some particles. So there we have the particles, and now we have the temperature being 300 kelvins. That's the temperature for this ideal gas, 300 kelvins. Then there is a pressure which is probably 8 point. The pressure, the temperature is 300 kelvins. The pressure is 8.29 atmospheres, and the volume is given by the volume of this container here, and then volume, and then the number of particles which we can count, right? I'm not gonna count them, but you can count them. And then those are the four quantities that you can measure. So let's change, for instance, the temperature. Change the, and then before we do that, remember that these four quantities, they are related by either this equation or this equation. Okay, so let's see, let's change the temperature. To change the temperature, we need to change the kinetic energy of the particles, and we do that by adding energy in the form of heat, right? So we do that, and now you see, now the temperature has increased. The temperature increases and hasn't changed because we haven't added any more particles, and the volume hasn't changed because we haven't changed the size of the container. So the temperature increases, the pressure has to increase, and the pressure has increased here to, sorry, this was 0.29 atmosphere, so now it's 0.45 atmospheres. And we can keep increasing the pressure and the temperature by adding heat. And we can cool down the system, and you can see that both the pressure and the temperature increases while the volume and the temperature remain constant. So we can also, let's cool down this system a lot. Let's see, let's bring it down. And then let's see what happens when we change the volume. Okay, we're going to change the volume, and when we change the volume here, right, we're changing the volume now, And you can see the pressure is now increasing. As we change the volume, we are not changing the number of particles, change V, so the pressure is going to increase and the temperature has to increase. Okay, so to summarize, we have three quantities: the pressure, four quantities: the volume, the number of particles or number of moles, and the temperature. And these four quantities are related by this either one of these two equations, and this is the equation of an ideal gas. So let's look at some problems to understand how to work with ideal gases. So if the volume of a sealed container of gas is decreased, the gas temperature, what does it do? Increases, stays the same, decreases, or not enough information? Take a minute to answer this question. Well, if the volume increases, right, so let's just take the ideal gas equation, PV is equal to nRT. We're going to write it as T equals to PV divided by nR. This is not changing, right? V decreases, but we don't know anything about P, right? So there's not enough information to answer this question. How about these two identical cylinders, A and B, contain the same type of gas at the same pressure. Cylinder A has twice as much gas as cylinder B. Which one is true? TA is less than TB, TA is equal to TB, TA is greater than TB, or not enough information to make a comparison. Take a minute and use the ideal gas equation. Okay, let's see. Well, we have PV is equal to nRT. So nRN, this is twice as much for B than it is for A. So this is two times, right? So this is the same, but this is larger. So therefore T must be smaller. So the right answer is TB is equal to TA. Two cylinders A and B contain the same type of gas at the same temperature. Cylinder A has twice the volume as cylinder B and contains half as many molecules as cylinder B. Which one is true? Well, which one of these is true? Take a minute to answer this question. And then again, we use the ideal gas law to solve this. We have PV is equal to NKT. We can use either one of the forms, right? So we write the pressure as NKT divided by V. And now we say this is half as large for A. And this is the same for both. And this is twice as large. So therefore, PA is equal to 1/4 PV. So So in general, the ideal gas problems will involve a sealed container. So that means the number of moles or the number of particles is not going to change during the problem. So in that case, you can write that PV over T is equal to nR. And then the gas is initially in some state I, and then is characterized for PI, VI, TI, and then some later time is going to be in the state F. So then you can use these equations to solve. So let's try that and see with this problem here, right? So we have two cylinders A and B, right? And they contain the same type of gas at the same temperature. Cylinder A, so they both obey PA. Let's just try this, right? They both obey PA. VA is equal to NA KVTA, right? And then PV is equal to VV equals to NV KVTA. And this B is not the same. This is just the constant the Boltzmann constant. So this is true for gas A, and this is true for gas B. Now we are being told that cylinder A has twice the volume as cylinder B. So let's rewrite this as 2VA, right, has twice the volume as cylinder B and contain as many molecules as cylinder A. And they are at the same temperature. So then you're going to get that this is PV times 2VA is equal to contains half, right? So 1/2 Na kVTA, right? So, and when you solve for PV here, then you can get that these two and this give you the 1/4 that is here. All right, thank you.